Hi, everybody. This is part 2 of the Week 9 After Party for Math 137. We're going to go through a few of the story problems that we didn't have time for in class this past week. So let's get right at it. In this first problem, this is number 7 from the notes. A ship leaves port at 1 p.m. and travels south 35 degrees east at a rate of 24 miles per hour. Another ship leaves the same port at 1:30 p.m. and travels 20 degrees west of south at 18 miles per hour. Approximately how far apart are the ships at 3 p.m.? All right, there's a few things going on here. First, we can get a geometric picture of the situation. We've got a port and two ships. Now, if we're going, we have some bearings here. We talked about bearings in class the other night. I remember we're supposed to draw a north-south line through our point P. This first ship goes 35 degrees east of south. And so if we're thinking about heading southeast, we're heading in this direction, and 35 degrees east of south tells us that this angle here is 35 degrees. All right, and then at 3 p.m., our ship is somewhere along this line. The second ship leaves from the same port and travels 20 degrees west of south. And so it's heading in a southwesterly direction. And this angle here is 20. The angle between the direction and the south line in this case is 20 degrees. And then at some point at 3 p.m., the second ship, let's call it ship A and ship B in this case. And then the question is asking how far apart are the ships at 3 p.m.? They're asking for this distance here. So we'll call this X. That's the unknown quantity in this case. So hopefully it's not too hard to see that we've got ourselves a triangle here. The 3 points PAB form a triangle. Didn't do a good job of tracing there. Let's go ahead and get this triangle off on the side now that we have an idea of the picture here. Let's pull this triangle off to the side and see if we can get some work done here. Now, this angle of the triangle, I got the red mark covering up, but that's 35 degrees plus 20 degrees. This angle here is 55 degrees. And we're trying to find the value X. Now, based on the work that we've done in class this past week, we know that we're supposed to be able to solve this triangle. And in addition to having some angles, we need some sides. Okay? Now, we should be able to figure out these two sides here. I'm going to call this side A. I'm going to call this side A and this side B just to kind of be, this side is the side that's opposite of corner A, and this is the side that's opposite corner B. Now, I guess the confusing part here is side B is related to the movement of the first ship. All right? Now, the first ship, it says it moves at 25 miles per hour. And if it starts at 1 o'clock, and travels till 3 o'clock, it travels for 2 hours. 2 hours at 24 miles per hour. And hopefully we know that that means that that ship has gone 48 miles. This rate, 24 miles per hour, tells us the ship goes 24 miles in 1 hour, which means in 2 hours, it gets to do that twice. So 48 miles. So B here, that means that side B here is 48. And similarly, the second ship, it starts at 1:30, and it's also traveling until 3, so it goes for 1.5 hours, and it's traveling at 18 miles per hour. So it goes for a full hour at 18 miles per hour, so it's 18 miles. and then it only gets to travel for another half an hour. So it goes 9 miles in that second half an hour. So the second ship travels 27 miles. So that's our second side here. 27 miles in a half an hour. Now, another way to get this is if you know the formula, if you took a physics class and know that velocity is equal to distance divided by time, then you can rearrange that to say that the distance is the velocity times time. That's another way to think your way through that part of the problem. Okay, now in this case, we have a side angle. Side is the information that we have. And if you remember, for a side angle side triangle, if we want to solve the triangle, we're going to end up using the law of cosines to do that. And in this case, it says, what it's saying here is that x squared is going to be a squared plus b squared minus 2ab times sine of the angle. Sorry, cosine. It's the law of cosines. I did this in the other video too. Times cosine of the angle in between them. Let's just call it 55 degrees, what it is. 55 degrees, not 55 squared. All right, so putting in the other two variables, x squared, well, let's just go ahead and get it all done at once. We have x will be the square root of a squared, which is 27 squared, plus b squared is 48 squared, minus 2 times 27 times 48 times cosine of 55 degrees. So remember, when the problems where we end up using the law of cosines, the calculator works a little bit obnoxious because there's a lot of pieces there. All right, so we have square root of 27 squared plus 48 squared minus 2 times 27 times 48 times cosine of 55. And I'm in degree mode still, and we're rocking and rolling. So the distance in between these two ships at 3 p.m. is about, I forgot to make sure that stayed on top. Is about, we'll call it 39 miles. We'll round this to the nearest whole number. 39 miles. All right, so that one wasn't too bad. Figured out where our triangle was pretty quickly. And this was a fairly straightforward, just find one of the sides of the triangle. I guess the hardest part here was using some information about the speeds and times traveled to figure out the lengths of those two sides. Moving on to the next problem. Height of a hot air balloon. The angles of elevation of a balloon from 2 points A and B on level ground are 28 degrees 50 minutes, 37 degrees 25 minutes, respectively. So I guess we've got, for trying to get our picture drawn here. And like I said in class, the WebAssign and the textbook will draw some pictures for you, but you kind of want to practice drawing these pictures for yourself because your exam problems are not going to have any pictures drawn for you. So there's 2 points A and B on level ground. And that allows us to say, all right, this balloon that's up here. Oops. Okay, I got a halfway decent balloon being drawn here. That's nice. Okay, there's my balloon. The person at point A is looking at the balloon, and the person at point B is looking at the balloon. It says the angle of elevation from those 2 points are 28 degrees 50 minutes from point A and 37 degrees 25 minutes from point B. It says that those 2 points are 13.3 miles apart. And we want to know what's the height of the balloon. So the balloon is at a height h here. Okay, so looking at this picture here, I'm not going to draw a second triangle because I think this one's good enough. I am going to Maybe zoom in a little bit so we can focus on our triangle. We're trying to find height h. And, well, first things first, if both of these angles are right angles, so that's one thing that's nice. So I've got two different right triangles that I might be able to work with. There's this first right triangle, and then a second right triangle over here. And it doesn't really matter which of these two right triangles we work with. Okay. Unfortunately, we don't know each of these triangles has a base, and we don't know the base of each of those triangles. And I'm not sure that there's a super easy way to figure out the base of those two triangles without knowing some other information first. Thing is that we might be able to figure out one of the hypotenuses. So there's two hypotenuses for these two right triangles, and we could figure out one of those two hypotenuses. All right. So for the big triangle that's made by the 2 points A and B in the balloon, we have two angles and the side in between them. We have an angle side angle situation, and that's one where we'll need to use the law of sines if we wanted to solve the triangle completely. Okay? Now, I think in order to solve this triangle completely, we're going to need to figure out this top angle. Okay? Because we can use, if I call this angle theta, we can say that, for instance, x over sine of 37 degrees 25 minutes is equal to 13.3 over sine of theta. And that's what we'll go ahead and do. All right, let's see, theta in this case will be 180 degrees minus the sum of those two angles, 28 degrees, 50 minutes, plus 37 degrees, 25 minutes. Looking at the calculator here sitting in front of me, I'm not exactly seeing the calculator I was working with the other night. Had a nice button that just had degrees and minutes and seconds on it. I don't see that button on this calculator. And so, I don't know. I'd have to look a little bit further. Let's just see if we can get this done by hand. All right, so if I add these two angles together, I'm going to take 10 minutes from that guy and give them to this guy and make 60 minutes. And then I'll take those 60 minutes and make another full degree, 29 degrees. So I got 29 degrees plus 37 degrees, 15 minutes. And the 29 plus the 37 makes, I'm going to take 1 away from the 37 and give it to the 29. 30 plus 36 give me 66 degrees, 15 minutes. All right. 180 minus 66. And now here's where I'll get the calculator going. 180 minus 66 is 14, I think, or 114. Yeah, 114, but I got to take another 15 minutes, so 113 degrees, 45 minutes. All right. Don't know what that was all about. Okay, so that's my angle theta, 113 degrees, 45 minutes. And so when I go to solve for x here, x will be 13.3 times sine of 37 degrees, 25 minutes, all over sine of 113 degrees, 45 minutes. All right, there should be another parenthesis there. All right, I'll do the calculator work off screen here real quick to get an answer. 13.3 times, well, I guess, no, it might benefit from doing this on screen just so that y'all can see what I do. Sine of 37 plus 25 divided by 60. That's how I basically convert the minutes to degrees, divided by sine of 113 degrees plus 45 over 60. Okay, so I get that x is about 8.829. But that's the x. I don't want x, I want h. But now I have all the pieces I need from the red right triangle. Okay, in particular, we can see that for the red right triangle, sine of 28 degrees 50 minutes is equal to h over x. So h will end up being x times sine of 28 degrees 50 minutes. All right, so I'll just take my previous answer from my calculator here, that's the x value, and multiply by sine of 28 plus 50 divided by 60. And that tells me that the balloon is about, we'll round it to the nearest tenth of a mile, or, well, no, I guess my original distance was given using 3 significant figures, so I'll give my answer with 3 significant figures, 4.26 miles. Okay, so that one was a little bit more involved in the sense that the thing that they were asking us for was not one of the sides or angles of the original triangle. We had to do a little bit more work there. But I guess we had a similar problem in class with the 2 mountaintops, where our end answer wasn't one of the sides of the triangle for the mountaintops problem. Looking at the next problem, parallelograms. Here it says a parallelogram has sides of lengths 30 centimeters and 70 centimeters and one angle of measure 65 degrees. So remember, a parallelogram is kind of like a tilted rectangle. Okay? In the sense that opposite sides are parallel, but the angles themselves are not right angles. I guess a rectangle is a special case of a parallelogram where all of the angles are right angles. So it says that the lengths here are 30 and 70. And then one of the angles has measured 65 degrees. That has to be this one. 65 degrees. All right, that means that this one is also 65 degrees. All right, now part A asks us to approximate the length of each diagonal to the nearest centimeter. All right, the diagonals here, there's this diagonal, and then there's a second diagonal from the other 2 corners. That way. I think the red diagonal is going to be the easier one to do first. There's a triangle that's formed by the red diagonal. Let's go ahead and get that triangle kind of isolated. I always like to kind of get the pieces that I'm focusing on. I like to get those off to the side. Once I get an idea of the big picture that corresponds to the story, I often like to kind of redraw the piece I need to focus on kind of off the side on its own. Okay, so we have a situation here where we have a side angle side triangle, and we're trying to find one of the opposite sides. We just got done doing one of those. This is one where we can use the law of cosines to get the job done here. In this case, x squared will be 30 squared plus 70 squared minus 30 times 70 times cosine. Finally got it right. Cosine is 65 degrees. So then x will be the square root of that. And the rest is going to be some calculator work. All right, let's get the calculator back in the picture. The square root of 30 squared plus 70 squared minus 30 times 70. Ooh, I wanted 2 times that. Did I make that same mistake before? Oh, God, I hope I didn't. Oh, God. Oh, I got the 2 there. Okay. It's supposed to be 2 times. I screwed up my law of cosines. The law of cosines would say, in one particular case, a squared is equal to b squared plus c squared minus 2bc cosine of alpha. So there should be a 2 here. Minus 2 times that. 2 times that. I almost forgot. All right, delete. All right, minus 2 times 30 times 70 times cosine of 65. And I'm going to go ahead and store that value under x. That makes the most sense here since I'm using x for that variable. But on my page, I'll go ahead and write it down as this is approximately 63 point. Well, they want us to approximate to the nearest centimeter. So I guess my answer here will be about 63 centimeters. Okay, so there's that problem. The other diagonal, there's a second triangle that looks like this with the blue diagonal in it. And we know a couple side lengths, 30 and 70, but none of the angles. And so you might be tempted to say that this blue line, it looks like it bisects the 65 degrees. I'm not so sure about that. I don't think it does. In fact, I'm pretty sure it doesn't. I'm pretty sure that it doesn't. All right. If it did, then this angle would be the same as that angle. And if those two angles are the same, that means that these two sides have to be the same. And they're not. Okay. So that blue line does not bisect those angles. Okay. So you got to be really careful about that. You know, your picture might lie to you. And so even if you have a guess, if it looks like your picture is telling you something, then it's reasonable to say, hey, it might be telling me that. But you got to be careful. What we want to use here is that the sum of all the angles in the parallelogram. Let's just go up to the parallelogram when we talk about this. Okay. If I want to think about this angle and call it theta. Okay. If I do 2 times 65 degrees. Now this angle over here also has to be theta. Plus 2 times theta. The angles in a parallelogram or a four-sided polygon have to add up to 360. And if you forget how that works, just think of a square. A square has 4 right triangles, or a rectangle also has 4 right triangles. 4 times 90 is 360. All right, so 2 theta is equal to 360 degrees minus 2 times 65 is 130. 230. I almost got a little bit lost in thought there. And that must mean that theta is 115 degrees. So now we can fill that in this triangle, 115 degrees. And I'll call this side length y, and we can use the law of cosines to figure out what y is in this case. Y is going to be the square root of 30 squared plus 70 squared minus 2 times 30 times 70 cosine of 115 degrees. Alrighty then, let's get the calculator back, get that done. Actually, I think I'm going to go up and reuse my previous, a lot of the numbers are the same here, so I'm going to go back and reuse this, enter, and then I got to go back and change 65 degrees to 115. That's all I got to do, right? All right, that was easy enough. This is about 87 centimeters if I'm rounding to the nearest centimeter. Okay, so those two problems weren't too hard if we were looking at them right. That's part A. Part B asks us to approximate the area of the parallelogram. And there's a couple of ways that we could go about this. First off, the parallelogram, if I were to drop a perpendicular down here, the area of a parallelogram is base times height. So if we were able to figure out what the height of this parallelogram was, that would be one way to go about the problem. Or I guess dropping it from this corner might be a better idea. All right. Actually, let's go ahead and do that. Okay? Actually, this is not going to be that bad. This angle right here is also going to be in 65 degrees. And we know what this side length is. So let's, oh God, we got a bunch of triangles here. Let's get the calculator off the screen so that we're not cluttering up so much. Got a bunch of triangles here. So this triangle that we're looking at is a 65 degree angle here. The hypotenuse is 70, and we're trying to figure out, that's our height h right there. And so we could say that, let's see, sine of 65 degrees is equal to h over 70. And so h, why do I keep writing these equal signs here? I hate it when students do that because these things aren't equal. These equations are not, well, I guess they are in a certain sense, but h will be 70 times sine of 65 degrees. All right, and then we could do that the area of the parallelogram is equal to the base, which is 30, times the height, 70 sine of 65 degrees. So that's one way to think about it. Another way is we have a bunch of formulas. We have a bunch of formulas. In particular, we have a formula that tells us that the area of this triangle, if you know two sides and the angle in between them, we have the area of that triangle is 1/2 the product of those two sides, 30 times 70 times the sine of the angle in between them. And the parallelogram is made up of two of those triangles. If I cut the parallelogram in half, there's two of those triangles. Okay? Or we could have also used these two triangles and done 1/2 of 30 times 70 times sine of 65 degrees. Okay? Now, so that's the area of the triangle part. And then the area of the parallelogram would have been 2 times the area of that triangle. 1/2, 30 times 70 times sine of 115 degrees. All right. Now, those of you who are thinking about what we're doing here, hey guys, we just proved that trigonometric formula for areas of triangles, or at least we proved this particular case of it, if you were wondering. All right, the proof of this formula looks a lot like the work that we just did. All right. Anyways, let's go ahead and finish this off. I guess the point being, don't do this other. If you know the trigonometric formula for area, you don't have to keep redoing that work over and over again. This simplified is 210 sine of 115 degrees, which according to my calculator, you guys don't need to see me type that one in. 210 times sine of 115 is about 190. And our units here for area would, since our lengths were given in centimeters, our units for area would be centimeters squared. All right, so I think that answers part B. By the way, as a calculus teacher, it had been a long time since I did any trig like this, and as a calculus teacher, I would always do this work anyways. Like, I didn't remember the trigonometric formula for areas of triangles or Heron's formula. Like, I told you guys the other day that this trigonometric formula for area doesn't have a name. The reason why it doesn't have a name is because nobody bothers to remember it, because it's not that hard to just do it by making triangles. All right. Okay, anyways, that's problem 14. And then one more problem, number 15 here. Finding the length of a cable. A vertical pole, 40 feet tall, stands on a hillside that makes an angle of 17 degrees with the horizontal. Approximate the minimal length of the cable that will reach from the top of the pole to a point 72 feet downhill from the base of the pole. Holy smokes, there's a lot going on here. I guess the idea here is we got a hill, and somewhere on the hill there's a pole that's vertical. So maybe give this pole a little bit of thickness. It says that the hillside makes an angle of 17 degrees with the horizontal. So if I dot in a horizontal here, that's telling us that this angle here is 17 degrees. The minimal length of the cable that will reach from the top of the pole to a point 72 feet downhill from the base of the pole. Well, I'm just going to go ahead and make this the point that is 72 feet downhill. And then my cable goes from the top of the pole to that point. Also, my pole is 40 now. Okay, so there's a rough picture of the situation here, and let's see if we can start to make some sense of this. Now, we're trying to figure out the length of this cable here. This is the value that we're trying to figure out. And I see at least a couple of triangles. Actually, I see 3 triangles involved. If I drop a perpendicular all the way down here, all right, there is a big triangle, a big right triangle, whose hypotenuse I'm trying to find. And that's all I know about the big right triangle for right now, at least. I've got a oblique triangle where I'm trying to find this length, and this length is 40. and this length is 72. But again, I don't know too much more information about that triangle. And then there is another right triangle wedged in below, where I know one of the angles is 17 degrees and its hypotenuse is 72. And that's all I know about that triangle. Okay, now there are at least two ways to proceed through this problem. The first way would be completely solve this right triangle, and once we get this right triangle solved, well, we don't necessarily need to completely solve it. We just need this side here, I'll call this A, and this side here, which I'll call B, and then this right triangle, the first one that we drew, has base B and height 40 plus A. 40 plus A, not 4 plus A. And we could use right triangle trigonometry and be done with the problem. Okay, so that's one way to proceed through the example. I'll let you go ahead and do that on your own because that's stuff that we could have done at the beginning of the semester. I think a better idea is, instead of completely solving this last right triangle, we know that since it's a right triangle, the other angle has to be 73 degrees. I have to add it to 17. Okay? And so up here in the original picture, 73 degrees there. In this oblique triangle, that angle here is supplementary to 73. So I'm going to go ahead and draw that, write that angle in here in this bottom. The angle that is supplementary to 73 is 107. All right? And now for this triangle, we have all the pieces that we need to use the law of cosines to find x. When I'm zoomed so far in, my pen is so thick. X is going to end up being the square root of 72 squared. This is a side angle side triangle. 72 squared plus 40 squared minus 2 times 70 times 40 times cosine of the angle in between those two sides. And that's going to be the answer to our problem. Now, yes, conceptually, that's a little bit more challenging than the other way that I described. But if you know the law of cosines, it's really like a two-step deal, or three-step. Find that angle, easy. Find that angle, easy. Use law of cosines, obnoxious calculator work. The other method I described, and again, I encourage you to look at that way too, and then you can make a judgment for yourself as to which you prefer. It's more conceptually easy, and it's something that you're going to be more comfortable with because it's all right triangles, but I think you're going to find that algebraically it's a little bit more obnoxious. And it's maybe slightly more work. But regardless of which method you prefer, let's see, when we get to our answer here, we get the square root of 72 squared plus 40 squared minus 2 times 70 times 40 times the cosine of 107. Now we're expecting our answer to be longer than 72, probably. Haven't done those kinds of reality checks so much. And it is. It is longer than 72. I don't know why I kept the square root symbol here. Do they tell us how we're supposed to round this? Approximate the minimal length. All right, so I'm going to go with about 90.8 whatevers. Sorry, 91.8. What are we looking at here? Feet. 91.8 feet. Or, I mean, if I wanted to do this to feet and inches, I know I got 91 feet. 91 feet. And then if I want the inches, I can take... Oh, God, how does this work? Got to subtract 91. And then I got to multiply by 12. Yeah. 12 over 1. 12 inches per 1 foot. So about 91 feet, 9 inches. Or maybe I'll say 9.2 inches. Okay. I think that's the last example that we have here, I'm pretty sure. Yep, that's all the story problem examples that I have. You guys have a lot of story problem examples on your homework, like I said. Please make sure that you give all those story problems your attention. Practice drawing some good pictures. If you run into any trouble with any of them, please let me know, and we'll find a way to get them worked through. That's all for this video. I'll see you guys next time.